So qualitative network models or functional models are obviously very useful and in some contexts, but ultimately you may need to do quantitative modeling as well. So if the purpose of constructing human environment systems requires more precise understanding and specification of the states of particular elements, quantitative functional models may be necessary. It's almost always necessary now. When constructing quantitative functional models, parts of the system are transformed into what are referred to as stocks and flows. As I mentioned, it's already known very well in chemistry and atmosphere, ocean and so on as reservoirs and fluxes, but they are still parts of the causal loops, thus the name stock and flow diagramming. This method for modeling systems provides not only for quantification but also a richer conceptual language than for causal loop diagramming. The elements are divided into stocks and converters. The dependencies are divided into flows and connectors, and two building blocks are added to form in the form of sources and sinks. I will show an example of the carbon cycle, which is the great example for what we mean by these words. A stock and flow diagram then would look like this, so it's still looking a bit qualitative, so we'll see carbon cycle with more numbers on it. So you have a stock, so you can think of this as the atmosphere where you are burning fossil fuels and creating CO2 inflow, and there are sinks, so ocean, land take up CO2, vegetation takes up CO2, maybe we are smart enough now to capture enough CO2 and so on. So you have sources and sinks, and you have a reservoir size that depends on how fast this is coming in and how fast this is going out, and there are causal loops associated with them as well. So let's say the stock size with some time delay affects an element like the atmospheric temperature, which then affects another element like water vapor, which will increase. So if CO2 stock increases, temperature increases, water vapor increases. You know, you have to think of social systems. I'm just comfortable with the physical system, so I keep giving physical system examples. Water vapor increases, then you have rainfall extremes increasing, not the total necessarily, or in other words, there is a exponential relation between temperature and humidity, but the relation with rainfall is complicated, but nonetheless overall globally rainfall should go up, and with the delay then you have a converter which may be like the river systems, groundwater recharge, sea level rise, or river, water that is being stored by human beings or not being able to be stored because rain is too heavy, and so on and so forth. So and then the connector will come back and maybe have a negative impact on the inflow. So this is a bit too schematic, but you get the idea that you have a system with elements and dependencies, and all these are one-way arrows, so we are always imagining one-way dependency, but in real world almost always there is a two-way dependency between the elements that we have been looking at, and so on and so forth. So a simplified example of a stock and flow diagram of cholera control in a refugee camp, which becomes a bit more realistic. So cholera cases, you have newly infected joining, and those that are recovered or not infectious anymore are going out, but in the meantime you have feedback from the number of cases with some time delay looking at attention of camp management, which has to go up as number of cholera cases go up, or go down as number of cases go down, and so on, which affects the resources allocated for cholera control, which affects the hygiene promotion campaign, let's say, and with time delay it can also affect hygiene practices among refugees. So that's a positive feedback, but it will have a time delay in terms of assimilating the hygiene information and changing habits and so on, which should have negative impact on the number of new cases emerging. So this is gives you a sense of what we mean, but of course this is still kind of a simplistic representation of it, because there are lots of other feedbacks that happen on how infected people use water and whether they contaminate the water, and then there is another feedback needed here to the attention of the management camp and so on. So once a quantitative model has been developed using stock and flow diagramming, it can be extended into a micro world by providing an interactive and user-friendly interface for users to experiment with the model. What does that mean? Basically, you can see if you artificially increase the number of incoming infected cholera cases, will they be recovering at the same rate, or will the system be able to give attention and find the resources and change the hygiene fast enough, and so on and so forth. So you can do perturbations once you have set the model up, so that you can see the what if scenarios of risk feeding into the system you have represented. Hence, microworlds are not so much a distinct tool for modeling systems as such, but for managing complex functional models, much in line with the relationship between causal loop diagramming and systems archetypes represented here. Okay, so don't worry if you don't get all the wordings, because it's a bit too descriptive. Examples are useful, but you don't get all the links, potential links. So here is a good example of the real world flow and stock diagram. So you have a stock of oil, gas and coal that is estimated in gigatons. So these will be gigatons per year. This will be gigatons as a total. So reservoir size, how much amount there is, and flux, how much is flowing out in unit time, typically at a global scale. So we are burning fossil fuels and producing emissions of around 10 gigatons of carbon per year. Land is taking up about 3.1 of that, 3.1 gigatons of that, but this is a flux, and you can see there is large uncertainties in measuring these. So those are parts of the risk calculations. And soils and permafrost have a stock of 3100 gigaton carbon. Land use change, deforestation, agriculture, urbanization, etc. are producing 1.2, but a large uncertainty in terms of a flux, so 1.2 gigaton carbon per year. And the vegetation holds 480 gigatons, so you can see relative sizes of the reservoirs as well. And you have surface sediments, coasts, organic carbon, so this could be just inorganic carbon. Of course, fossil fuel is hydrocarbon, but it's inorganic, whereas here you have things like phytoplankton, biomass and so on. And you have marine biota itself carrying some small amount of carbon, and of course the ocean, deeper ocean, has a huge, the largest of all reservoirs in terms of dissolved inorganic carbon. So when organic carbon gets respired, it gets converted into inorganic carbon, which could be like calcium carbonate and so on. So in the atmosphere you have certain stock, 875 gigaton carbon per year, but you are adding lots of human activities adding here. Ocean takes up some 2.9 gigaton carbon per year, with some uncertainty. So this gives you a sense of how much we are emitting, how much is being taken up, and they are on an annual, these are typically averaged over a 10-year period, so there is always a time delay. When you burn, you are immediately releasing CO2, but land uptake is slower. Atmospheric increase is almost immediate, but not quite, because there are slow sinks of ocean and vegetation and so on as well, right? So this gives you a good sense of the functional system archetypes and flows and stocks, and this is modeled fairly well right now, but obviously data will be missing, so there are many other details. I have a full course on global carbon cycle on my YouTube channel as well, if you wanted to follow up. So this is probably a bit short. No, it's okay, 9 minutes. So let's leave the modeling and the definitions behind and come back and read the conclusions with appropriate comments from me. Okay, so that will conclude this chapter on constructing human environment systems. So we defined a bunch of things to construct models and types of models and modeling approaches, and we'll now move on to the next section on how to approach the world, from how to approach the world to how to change the world. Okay, see you in the next podcast.